share my screen. All right, so here we go. Last lesson in the fall semester. All right, so for 8.6 and 8.7, we're talking about something called parametric equations and graphs, okay? And so we're going to be using the same XY plane that we've used for a really long time, okay? So we're not using the polar graph with the circle, okay? We're just using a regular XY rectangular or Cartesian plane, okay? But in math, sometimes we have functions that are like pretty crazy looking, okay? So it's not like just a line, it's not just a parabola, it's not even like something with vertical asymptotes and holes, or it's not like sine or cosine, but it actually might look like one of these three examples down here. Okay, so it's sort of like a very wiggly, all over the place. It might cross the same graph by itself. It might go all the way around and come back and meet at the same point. Okay, so we have a lot of different possibilities. And one thing that we're going to find is that with these kinds of graphs, it's actually really important that we have a way to define them. Yeah, I think, Vanessa, that's actually a really, really good point. They do kind of look like racetracks, right? And so when we have curves that are maybe a little bit more complicated like this, then we want to have a different way to define them, okay? And we want a different way to define them so that when we get to finding things like the length of the curve or the area inside the curve, that we actually have ways to do that where we're not going super crazy with all of the different computations, okay? And so that's where we're starting today. So a plane curve is a set of ordered pairs. Okay, so we're going to look at a lot of ordered pairs today, where f and g are functions defined over an interval, okay? And so what we're going to find is that when we're plotting our graphs, not only do we want to plot them like we can see in A, B, and C here, but we also want to think about the direction in which we're going, okay? So for example, in this curve here, all right, the one that just says curve, we start at P of A and we finish at P of B. And so if I were to sort of think about the direction of this curve, I'm going to start here and I'm going to sort of move along in this direction. It's going to do a little loop and come back out and finish off at this end point. Okay. Now, in B and C, it's a little bit harder to tell the direction. We know that we start here and we actually stop here, but there's no arrows to tell us which direction we're going in, okay? So maybe we're going this way, right? We go this way and then we come back and we come back this way, right? That's one possibility. But the other possibility is that maybe we start at the black dot and we go in this direction. We kind of go this way and then this way, and then we finish here, okay? So the diagram as it is for B is not super clear. It doesn't tell us the direction, okay? And same thing for part C, it doesn't tell us the direction. And so one thing we're going to be really thoughtful about in our graphs is we're going to make sure that we not only can plot the picture, but we can also tell who's ever looking at our work the direction in which we're going, okay? And so this is where this idea of parametric equations comes into play, okay? So let's say we have a curve and it has all these ordered pairs, f of t and g of t, and we define them over an interval, okay? So this interval means that we have a starting point and we have an ending point. Okay, so we have a starting point and an ending point. And that's going to be really important for us to think about, where do we start, where do we stop, and what direction do we travel in to get there? Okay. Now, when do we use parametric equations? Folks actually use parametric equations quite a bit when they're defining motion of an object. Okay. Um, And let's see, there's a question here. So basically the x-axis of a parametric graph is the y-axis of its function. I'm not really sure what you mean by that. So maybe think about if you could reword that for me. Okay. But when we're thinking about these kinds of graphs, a lot of the time we're talking about how something moves over time. Okay. And so that T, we use T because a lot of times we're talking about time. We want to know how things move over time. So whether it be you are throwing a ball in a given direction, so where is that ball over a period of time? Or you're tracking the motion of a particle. So where is that particle at a given moment in time? Exactly. And so it lends itself to the idea of velocity and speed and things like that as we think about application. Okay. Now, we are not going to get to a ton of applications. We're mostly just thinking about the fundamentals, like how do we get these graphs? How do we know what direction they're in? And then sort of finishing off with like just a little bit of a reference sheet. Like we're going to see so many different kinds of equations. So how do we know what they look like? Kind of like we know, okay, y equals x is a line, or y equals x squared is a parabola. Okay, so thinking about when we get to Calc 2, which is when you'll see this again, how do we know what shape it looks like? Okay, and we are going to spend a lot of time with tables today because I think it's always a really good fallback to think about. I can always plot points to figure out what my graph looks like. Okay, so let's go ahead and get started here. So we're going to take a look at a couple equations, all right, with 3 examples, and we're going to go ahead and create a table, and then we're going to plot the points, and then we're going to plot them, or plot the points, and then we're going to connect them with arrowheads that show us a given direction of the path, okay? And how coordinates are written if f of t, g of t, x, y value is of the ordered pair. Yes, I think that's actually so x of t will give you the x value of the point. It does not give you the y value of the point. Okay. Well, let's try this example and kind of see where we get, okay? All right, so let's start with our equations. So in this case, we have x of t equals t minus 1, okay? So x of t equals t minus 1. And we have space in our table for x of t. And then we have a second equation, y of t equals 2t plus 4. And then we have a space for us to fill in the y of t, okay? So in order to think about plotting points, I'm going to need an x value and a y value. That's why they give us 2 equations, one equation for the x and one equation for the y, okay? Now, if I just saw the pink equation by itself, what shape do you think that would be? If I just had like t minus 1 or x minus 1, what shape would that be? It'd be a line, yeah. Okay. What about the blue one? If I have just like a 2t plus 4, what shape is that going to be? Yeah, it's going to be a line. Okay. So we know what they look like individually, but then the question is what happens when we put them together? Okay, so let's kind of plot these points out and see what we get. All right. So what values are we going to plug in? Well, we're going to plug in, let's see. We're going to plug in a -3. We're going to plug in a -2, a -1, a 0, a 1, and a 2. All right. Where am I getting these values from? Like, how did I just randomly pick -3, -2, -1, 0, 1, and 2? Okay, exactly. Just like Thea said, they're in the given interval, meaning there's this last part of information here that kind of tells us what values we should plug in. Okay. Now, what that means is that when I'm plotting the points, the first one that I get, when I plug in -3, whatever point comes out of there, that's going to be the starting point. And then we're going to go to this point, then this point, and then this point, and then this point, and we're going to finish with the last point in the interval. Okay? So we're going to plot 6 points, and we need to connect them all together, and we want to go from 1 to 2 to 3 to 4 to 5 to 6. Okay? So let's plug in these numbers. I'm going to take -3. I'm going to plug it into the pink equation. So -3 minus 1 gives me -4. I'm going to plug in all the other points, -2, -1, 0, 1, and 2. Okay, that'll give me -3, -2, -1, 0, and 1. Okay. Any questions about how I got those values? Okay. Now let's figure out how to get the y values from the y of t. So we're going to take all those orange values, we're going to plug them into the blue equation. Okay, so we're going to plug in -3. So 2 times -3 is -6, plus 4 is -2. -2 plugged in gives me 0, and then 2, and 4, and 6, and 8. Okay. So I'm plugging in the orange values into the blue equation. Right? So now I have 6 coordinates that I can graph. My starting point is going to be at -4, comma, -2. This is point number 1. Okay. Let me plot those other 5 points. So I'm going to go to -3, comma, 0, -2, comma, 2, -1, comma, 4, 0, comma, 6, and 1, comma, 8. All right. Any questions about how we got those 6 points? Okay. So what do we do now? Well, we're going to connect the 6 points, but we're going to be really careful about how we do this. I have to start at the first point, and I have to stop at the last point. Okay. If you draw anything longer than this, that's wrong. If you draw anything shorter than this, that's wrong. Okay. So this interval right here means that we don't have a line. So it's not a line, but a line segment. So it has to have a start, it has to have a stop. Okay. So let's say on the exam, you fill out your table, you plot your points, and then you submit your work like this. This is not full credit. Okay. What am I missing? What are we missing here? Yeah, we're missing arrowheads. Okay. Now, I know this is kind of a silly question because we just talked about arrowheads, but it's like the number one thing that folks forget, okay? So when we're drawing this, we have to show direction. So I'm going from point 1 all the way to point 6, so I have to just draw a few arrows. It doesn't really matter how many, but in that direction. Does that make sense? So by arrows, I don't mean arrows at the end like a regular line. I mean, show me the direction that this is moving in. Okay, so we're starting at 1, we're going to 6. We throw a few arrowheads in there along our curve to show the direction of the curve. Okay. All right, so, well, this one was pretty straightforward. We started with a line and a line, and we thought maybe it would make a line, and it did. It made a line, but specifically it made a line segment. Okay. So let's kind of move along and try this out with 2 other examples. All right, so we've got example 2 here. Let's do a little bit of color coding. So we know we have an x equation, and we're going to plug in a bunch of points into the x. We know that we have a y equation. We're going to plug a bunch of things into the y, right? And yep, looks like we've got a parabola and a line. And so the question then is, what shape does that make? Okay. And then we want to make sure that we think about the interval, because the interval tells us where do we start and where do we stop. So we're going to start at -2. We're going to go all the way until we get to 3. Okay. And then we'll have 6 points like we had in number 1 to go ahead and plot. And we're going to plot those points. We're going to connect them. And then we're going to include the arrowheads. All right. Oh, what about number 3 here? Looks like we have an interval. Looks like we have an x, which is going to go here. Looks like we have a y that's going to go here. Okay. Now, for the t values, I did start at -1 and I went all the way to 2, but I didn't count by 1s. I actually counted by a half. Okay. And so, yeah, I'm actually really glad you asked this question. We're going to give an interval, no matter how big or small. It's not that we're trying to find 6 values, okay? It's not that we're trying to find 6 values, but sometimes it's nice to find a few more points so that we get a better idea of what the graph looks like. Does that make sense, Thea? So it doesn't have to be 6, but sometimes when we only plot 2 or 3 points, it's hard to tell what it looks like. So sometimes it's nice to sort of get some more points in there. Okay, so that's why in this case, I didn't just go by like ones, but I also wanted to show us that we could plug in fractions and that's okay. Okay, but we're going to do the same thing. We're going to plug those points into the X. We're going to plug those points into the Y. We're going to get a bunch of coordinates. We're going to plot the coordinates and we're going to trace them. Okay. And so my question to you, because I think the process itself is not necessarily super hard, but we have in number 2 sort of a parabola and a line, right? We have the t squared minus 3 and then a 2t plus 1. And then in number 3, we have a line and a parabola. Okay, so we have like the 2t and then the t squared minus 1. What shape do we think number 2 is going to end up being? Okay, something with curves. Okay, a sideways parabola. Okay, so those are some good guesses, right, about what it might look like. What do we think about number 3? What kind of shape do we think we're going to get out of number 3? Parabola. Okay. Okay. So what I'd like us to do now, because I think we can all sort of plug points in and plot those points, is I'm going to have us go out into some breakout rooms, okay? And I'm going to have you work on number 2 and on number 3. So you're going to find a bunch of values, you're going to plot them, make sure everyone's kind of got the same graph. But after you have your graphs, I want you to think about the shape that you get at the end. Like, does that make sense with our guess? Does it not make sense? All right. And so let's go ahead and I'm going to stop sharing my screen here. Right. And so we're just going to go out into some breakout rooms. I think maybe no more than like 10 minutes to kind of plot those. If you and your group finish 2 and 3, you're welcome to move on to question 4. Okay, so if you and your group finished early, you're welcome to move on to question 4, which is pretty similar in terms of just like finding some values, plotting some points, and seeing what it is. Yes, that, let me make sure that I've got that down. Whoops. Okay, I think I've got the settings done. Let's, all right, looks like most of us are back. We'll just give the other folks a couple more seconds to trickle back into the room. All right. So I know that there was a question, but we were so close to the end of the time, I thought we could just kind of answer that question here. Which room had a question and what was your question?
Our group just wanted to like check to make sure we did it correctly. That's all.
Perfect. Well, we're going to check those over right now. Okay, so for number 2, once you plug the orange values into the pink and the blue equations, you should get these points and it should look something like what we have plotted next to it, okay? This is what most groups were getting. Yes, no, maybe so. Yes, okay. So I think in some senses we were kind of right that we did get a parabola, maybe not the whole parabola, but we got part of a parabola, okay? And so when we had the x squared and then the y, we actually end up with a sideways parabola, okay? Oh, no wonder it didn't look right. 1, -3. Yeah, thank you. Okay, so when we're connecting these, again, we just want to make sure we start at a given point, we stop at a given point, and then we have the arrowheads to show the direction, okay? And then I had you take a look at question number 3, which was sort of similar in the sense that we had a line and a parabola that we were plugging our t values into, but this time we ended up with not a sideways parabola, but a regular parabola, or at least part of it. Okay. So I'll give you a moment to check that over, make sure you've got the same graphs that I have here. All right. All right. So we can see that some of the shapes that we know can actually inform us about what we're going to see, okay? But sometimes it's not quite so clear. And so let's take a moment to take a look at question number 4, okay? So I got started on this one while you folks were in the breakout room, okay? So it follows that same idea. We've got the x equation, we've got the y equation, and we have an interval, but this time our interval is from 0 to 2 pi, okay? And so let's start with this idea of plugging things into a table, all right? So, you know, in 2 semesters or in a year or whenever or never, depending on who you are, but if you do take Calc 2, knowing that you learned this once upon a time, but you can always come back to the table to help you figure out what shape things are, okay? And so I started plugging in a few of the points, 0, pi over 6, pi over 3, pi over 2. Okay, and I got these values, and I'm going to go ahead and start to plot those points. Okay, so the first point I'm going to plot is 4, 0. Okay, it's not, but okay. We're going to go next to 3.5, 2. I said ish because we're graphing these and I didn't think the scale was big enough to go to like the 3rd decimal. Does that make sense? Yeah. Okay. And then 2, 3.5-ish, and then 0, 4. Okay. And so that's all we have so far. And we have those few points. Okay. Now, you're right. Maybe it is the cosine graph. It's not, but maybe it is, right? We don't know enough at this point to say for sure what shape it is, okay? So maybe it would be beneficial to plot a few more points, all right? So maybe we could use 2 pi over 3, and then 5 pi over 6, and then we'll get to pi, and let's just kind of see what we get there, okay? So if we use our unit circle values, let's see, we plug x into 4, cosine of 2 pi over 3 will give us -2. When we plug in 5 pi over 6, it'll give us -3.5-ish. And when we go to pi, we'll get to -4, okay? And now when we plug the values into the sine equation, let's see, we're going to get 3.5-ish, 2, and 0. Okay, so we have a few more points to plot. All right, let's try these out. -2, 3.5. -3.5, 2, and -4, 0. All right. Now, at this point, Ethan could still be right. It could be the cosine curve. It's not, but he could be right, right? So let's plot some more points and see what we get, okay? 7 pi over 6, 4 pi over 3, 3 pi over 2. And let's see, I think we get negative 3.5, negative 2, and 0. And let's see, negative 2, negative 3.5-ish, and negative 4. All right, let's plug in some of these values, plot them out, see what we get. Negative 3.5-ish and negative 2, negative 2 and negative 3.5-ish, negative 0 and negative 4. All right, Ethan, would you like to revise your guess? Or have we just crushed you and you don't want to talk anymore today? Ah, it is a circle. Very nice. Okay. I want you to be really careful about your language here. All right. So I don't know that we really know anything about slope yet. All we've done is just plot points. Okay. So if I plotted the rest of it, my guess is it would be, whoops, not there, but it would be like here and here. Okay. No, it's not a question mark. All right, so we can tell from here that we sort of keep going all the way around, and when we get to 2 pi, we're going to get back to where we started, okay? And so if we think about drawing our circle, then we're going to start here. We're going to come up to the highest point on the circle, and then we'll go out to the leftmost point, and then we'll go down to the bottom, and then we'll get back to where we started, okay? Now, just like the other graphs, though, we want to make sure we have our arrowheads here. And I always put that in the directions, but somehow folks skip over that part, okay? So let's think about where our first point was. So point 1 was here. And point 2 and 3 and 4 were like here and here and here, okay? Once you have the general direction, then you can go ahead and put in your arrowhead. Okay. So turns out this is one of the other sort of common equations that pops up in parametric form, where we have the sine and cosine. And as soon as we see sine and cosine, we're generally thinking things that have a curve, maybe a circle, but maybe like the cosine graph, maybe the sine graph, okay? But actually, when we see trig functions in here, we're actually going back to our conic sections. So for those of you who took Math 116, when we learned about our conic sections, we learned one way to describe conic sections. And those equations were super long. We had to complete the square a whole bunch. But when we look at the parametric equations for conic sections, they tend to be nicer. Even though there's two equations, it will be easier to work with these two equations when we get to calculus than it is to work with the very long ones that we had from Math 116. Okay. What do you think might happen if I take the cosine and the sine and I just switch them? So my pink equation was 4 sine t, and my blue equation was 4 cosine t. Let me ask that question one more time. So if I have 4 sine t for x and 4 cosine t for y, what do you think might change about the graph? Okay. Yeah, I think Isis, you really got that one. It is switching the directions, okay? Because we're really taking the x and y points and we're switching them, which means we're plotting them in the opposite order, okay? And so if you have the same number in the front, that 4 and 4, okay, and you have a cosine and a sine, it turns out that you're going to get a circle, all right? So if you have sine and cosine in the x and y, and you have the same number in front, you're going to get a circle, okay? The direction that you trace the circle is different depending on which one's cosine and which one's sine, but you'll still get the same shape at the end, okay? Now, back to Yitan's question. So if the amplitudes are different, all right, so if we're thinking the number in the front, like 4 and 4. So if we have 4 and 3, do we think we're still going to get a circle? Yeah, if we had like 4 and 1, we wouldn't get a circle. We would get, what is the name of that shape? All right, let's think back to our mathematical language here. We don't call it an oval. What do we call it? Yeah. Okay, so it turns out that, Ethan, you're right. If you have two numbers in the front and they're different from each other, but you still have the sine and cosine, you're going to end up with an ellipse. Okay, and so that'll be a really, when you look at these equations, you can say, oh, I know this is going to be a circle, or oh, I know this is going to be an ellipse, right? Okay. So I think this is a good time to take a break, all right? So the first part of class, we've done plotting points, making a table, drawing the picture, okay? For the second half of class, what we're going to focus on is something called eliminating the parameters, okay? So what we're going to do is we're really taking our parametric equation and we're putting it back into rectangular form. Now, unlike polar equations, this is going to take a little bit more thinking because we have to go back to all of the algebra skills we've ever learned. Think about that as a toolbox and think, okay, what might be the best way to go about this, all right? And I know those kinds of questions are always harder because it requires you to remember a lot of stuff that we've done in the past, even if we haven't done it recently, okay? So let's take a break right now. It is 10:40. Let's be back at 10:50, okay? I'm gonna stop sharing my screen. Sorry, hold on a sec. Okay, here we go. All right, so one thing that we should feel comfortable doing is plotting points, using the equations to generate some points, plot the points, and then draw a diagram, okay? The other half of what we're going to be covering is something called eliminating the parameter, okay? And as I mentioned before break, what this means is what we're doing is we're rewriting our equation in rectangular form, Okay, so what we want to do is we want to get rid of t. Okay, so we want an equation that is just x's and y's and no t's. All right. So I'm going to go ahead and copy down the equations we had. We had x equals 4 cosine t and y equals 4 sine t. Okay. So if we want to get rid of the t's, all right, that's one thing we want to do. The other thing we want to do is we want to turn two equations into one single equation. Okay. So we not only want to get rid of t, but we want to condense into one equation, right? Now this first one I think is a little bit tricky to think about, so I'm going to walk you through this one, all right? But as we do the other examples, I really picked those examples to highlight some different tricks and techniques that we're hoping to see, okay? The ones that are like most commonly used, that's what we're going to be looking at, okay? So for this one, I want us to kind of think back to one of the things we learned earlier this year, all right? So we're going to go back to some of those identities, all right? Now, I know some of you are like, ugh, identities, I thought those were done with. They're not, they keep coming back. That's why we spent so long on them. All right, but one of the most common identities we learned about was that cosine squared of theta plus sine squared theta equals what? Equals 1, okay? Now this is probably like the most common trig identity. So that's why I'm like, okay, like out of all of them, know this one, all right? So we know that cosine squared plus sine squared equals 1. But what we can do here is that means that if I have cosine squared t plus sine squared t, that's also going to equal 1, okay? Now, when we write cosine squared t, what are we actually saying here? Like, what's another way of rewriting cosine squared? Not with the identities, but just like algebraically, what does it mean? Yeah, it means cosine times cosine. Or we could write this as cosine t squared plus, and we could do the same reasoning for sine. We'd have sine t squared equals 1. Okay. Now, why would I use this identity and why would I rewrite it like that? Because we've talked about how nobody ever writes the cosine squared like cosine t with the squared on the outside, okay? Well, here's why. Let's take a look at this equation, our x equation, okay? And let's go ahead and maybe take a look at it over to the right. So we know that x equals 4 cosine t. Well, look what happens when I divide both sides by 4. Okay. Well, why is that so important? Well, it turns out that we can use this and substitute, okay? So everywhere I see a cosine t, I can replace it with x over 4. Does that make sense? Everywhere I see a cosine t, I can replace it with x over 4. All right, so let's make that substitution right now. X over 4 squared. Okay. Now that got rid of one of the t's, which is good. Now my question is, how do I get rid of that sine t, right? I don't want sine t, I want something with x's and y's. Well, let's see what happens if we apply the same kind of reasoning, okay? And I say that we just kind of want to see, because I think it's important that we don't sort of like assume that one thing we do somewhere is exactly the same we could do somewhere else, okay? And so let's write this one over here. Y equals 4 sine t. Well, let's try dividing by the 4 again. Y over 4 equals sine t. And so that looks like everywhere I see sine t, I can replace it with y over 4. Okay, yeah, exactly. So now let's take a look at what this is right now. Does this have any t's? Ah, it sure doesn't, right? We got rid of the t's. Okay, so check, we did that. Now, do we have everything in one equation? Yeah, we do, right? It's x over 4 squared plus y over 4 squared equals 1. So we fulfilled our requirements, which is get rid of the t and condense it into one equation, okay? Now, this means that we have eliminated the parameter. And what we have now is an equation in rectangular form. It has x and it has y, okay? As a little side note, all right, I just want to expand this equation a little bit, all right? So x squared over 16, so I square that term, plus y squared over 16 equals 1, okay? Now I'm going to multiply both sides by 16. So I get x squared plus y squared equals 16, all right? Now, why would I do that? Okay, the reason why is I just wanted to show us that this form of the circle equation that we learned back in Math 116, x squared plus y squared equals r squared, is the same as our parametric equation, x equals 4 cosine t and y equals sine t. Okay. Yeah, in this case, we know the radius is going to be 4. All right. And turns out this number and this number, when they're the same, they tell us where the radius is or how big the radius is. Okay. And so that's sort of another reason why when those numbers in the front are different, we got like a 4 and a 3 or like a 4 and a 1. It's not going to be a circle. It's going to be an ellipse, like Ethan said, right? It's going to be an ellipse because we don't go out the same distance in the x direction and the y direction. Okay. So a lot of this does kind of come full circle from what we learned like a few months ago, right? Okay, so just to summarize though, in order to eliminate the parameter, we need to get rid of the t and we need to condense it into one equation, right? And the way we do that is going to change based on the information we have, right? So before we move on, are there any questions on example 5 right now? Okay. All right. So let's move on. Let's kind of combine what we learned before, the plotting and the graphing, and the idea of eliminating the parameters to kind of predict what shape it is. Okay. So we're still going to have a picture at the end, but we're going to end up thinking about that picture in terms of the equation we get, that is the rectangular equation, okay? So we still have two equations. We've got our x of t and we've got our y of t, okay? Now, I think one of the hardest things about math is that there's so many symbols, and in order to be able to sort of understand the question, we really need to know what those symbols are, right? And so in this case, this says T is in R. So we could also say T is an element of their script R is like my R with the double line, okay? And all that means is that T can be any real number. Yeah, that's a script R. I know. Here, let me zoom in a little bit. Yeah, I know. And every sort of textbook does it differently. That's why I just draw the double line there. It is very Shakespearean. Okay. But the thing is, if we're looking at all real numbers, that means that we don't have like a set of numbers that we can plug in because we want to plug in all the numbers. And so instead, let's think about what shape this might generate. Okay. So we have x of t and we have y of t. What shape do we think x of t is going to look like? And what shape do we think y of t is going to look like? Yes, I'm okay. Thanks for checking. All right. What shapes are coming to mind? Yeah, a parabola and a parabola. Okay. So if they're both parabolas, what do we think the end shape is going to be? An ellipse? Maybe. Okay. So this is the thing, right? We're not used to working with parameters as much, right? Two separate equations to get one picture. So the first time we see things, yeah, we might not know what they look like, right? So let's eliminate the parameters. Let's see what the rectangular equation looks like. Because I bet if we have the rectangular equation, right? I bet like if a number in the previous problem, instead of doing the table, if we had done the equation first, I bet we would have seen right away that it was going to be a circle, okay? And so let's kind of do that same thinking here for number 6, all right? So let me write out the two equations. X equals -2 plus t squared, and y equals 1 plus 2t squared. And actually, one of the reasons that I write my T's with the tail like that, I think some people write T, the letter T like this, but then it kind of looks like a plus sign. So that's why I make a little tail on my T. So I know it's a T and not a plus sign. Okay. You don't have to do that, but it's just something I've made the mistake plenty of times where my T turns into a plus sign and then I'm missing some variables. Okay. So let's think about this. I'll tell you for this one, we do not need to uh, use any trig. Okay, so no trig identities. Whew. So our goal is still the same though. We want to get rid of the t's and we want to have one equation that has x's and y's. And typically we use this idea of substitution, right? So we sort of like take one equation and we substitute it into the other one so that we can turn it into one equation. And hopefully the t's kind of go away, right? So take a moment, look at these two equations here. What kind of substitutions could we make? Okay. And so it seems like there's sort of two ideas here. The first idea is we solve for t in one equation, and then we plug that into the other equation, right? So if I were to solve for t, okay, let me just write that out in purple. If I were to solve for t, I would get x plus 2, and then I take the square root equals t, right? And then I plug that into the other one, I get y equals 1 plus 2 square root of x plus 2 squared. I think that's what Richard and David and Natalia were saying, right? You solve for a t, you plug it into the other one, okay? I think as a general strategy, that's not a bad idea, okay? So when we think about in general, I think that we can solve for t, plug it into the other one, okay? In this case, though, if we work this out, we'll get 1 plus 2 times x plus 2, right? Because a square and a square root, they cancel each other out, okay? And so we get an answer. This would be our answer. Now, one thing that Eric and Gloria were saying is like, maybe, yeah, okay, well, I'm just gonna read this because I think it says it better than I did. You shouldn't solve for more than you have to, right? There's this idea of working more efficiently, which is in this case, we happen to have a special situation where we have a t squared in the one equation and we have a t squared in the other equation. So really, we could just solve for t squared and plug that into the other equation. Okay. So if we tried that method, we would get t squared equals x plus 2. And we'd substitute that into the other equation, y equals 1 plus 2 x plus 2. Now that's the same thing that we got in the purple, right? Same thing. The one in the purple, just we had to square root it and then we had to square it. Okay, so I would say that either one is mathematically fine, but I think as Eric points out, we really want to start to think about like, how do we do things efficiently? It's not that some ways are wrong, it's that some ways are more efficient than others, okay? All right, so now that we have this rectangular equation, y equals 1 plus 2 times x plus 2, what shape is that? Yeah, it's a line. So it turns out that we have one parameter is a parabola, the other one is a parabola, but when we combine them to make a rectangular equation, we don't get a curve, we actually get a line. Okay. Now that's kind of a cool pattern because I'll tell you that if we had something like this, let's say x equals negative 2 plus t to the 10th, and y equals 1 plus 2t to the 10th, we would still get a line. And if I did this, instead of powers of 10, if I had powers of 100 in both of them, I would still get a line. And if I change those powers to just like third power, I'd still get a line, okay? Let's see, so could a possible hypothesis be both equations had the same highest degree? Okay, yeah, so that matching degree, if the degrees are matching there, okay, and that's probably better, the highest degrees are matching, then we're going to end up with some sort of a line. Yeah. Okay. And so let's kind of think about what this graph might look like. And let's kind of actually graph this one. So y equals, let's see, 2x plus 2 plus 2. 2 times 2 is 4 plus 1 is 5. Okay. I think y equals 2x plus 5 is easier to draw than making a table, plugging values into the pink equation, plugging values into the blue equation, and then plotting all those points. Okay. So 2x plus 5 means I have a y-intercept of 5 and a slope of 2. And the only reason we could really say slope here is because it's a linear function, okay? So with the other ones, they're not, the slope actually changes at every single point, so we can't necessarily tie that back to the language of slope. But when we have a line, then we can talk about things like slope, okay? Now, how many points should I plot? Yeah, it is all real numbers, meaning every single number, as long as it doesn't have an I in it and it's not imaginary, I could plot. And they would all be along this line, okay? And so it's all real numbers, so I can go ahead and just kind of connect everything. And I could have arrows on the end because it's going to go forever and ever. And it turns out that in this case, if you sort of used a table to plug in some values, you would find out that the arrowheads that you draw on here would actually be in both directions. So you would start going in one direction. At some point, you would turn around and come back to the other direction. Okay. Yeah, so this interval is now opened up to be every single real number. Okay. All right. So let's take a look at example 7 here. All right. Let's take a look at example 7. So we do have a bunch of equations, right? We have our pink equation, we have our blue equation, and unlike the other one, we actually have an interval. So we want to start at t values of -2, and we want to stop at 6. So there should not be arrows at the end of our graph. We want to just draw that particular set, okay? So let's think about how we could eliminate the parameters, right? So we have x equals the square root of 2t plus 4, and y equals 2t plus 1. Maybe a parabola. Okay. So let's think about how can we get rid of the t's? How can we combine these equations and get rid of the t's? Okay, so one idea is solve for 2t, okay? So sounds like you're taking a page out of the reasoning from our last problem where we could get all the way down to where we isolate t, but then we sort of had to like square root and then square it again. Or we could do what Gloria had said, where we just isolate that t squared, right? Like t squared was a common term between both equations, okay? Yeah, so let's see. We have a common term this time of 2t. So it does sound very reasonable that we should isolate the 2t, and we can do that by squaring the equation and subtracting the 4 and then substituting, okay? So let's try that. This will give me 2t equals x squared minus 4. So I'm going to go ahead and substitute that into this equation. So y equals x squared minus 4. That goes in for the 2t, right? Plus 1. And we could even say x squared minus 3. Okay. We know what that looks like. We know that that looks like a parabola, yeah? And what is the graph transformation that happens to this parabola? All right, it is not to the right 3, folks. It is down 3, okay? So I know we spent a lot of time doing like super complicated graph transformations, but this is the kind of context in which it comes up, all right? So you have x squared minus 3. Folks are going to expect you to know what that looks like. Parabola moves down 3, okay? So it's not going to be really as complicated as what we did in Math 116, but we want to have that basic fluency there, okay? So I could, on my graph, sketch a parabola that has moved down 3 units. But what I need to be careful about is this is only going to give me part of the parabola, okay? So it only gives me part of the parabola. So I have to draw the correct part, all right? So here's what we're gonna do. We're gonna take -2, okay, which is the lower end of the interval. We're gonna plug that -2 into the pink equation and the blue equation, okay? So when t equals -2, x equals, let's see, -2 times 2 is -4, -4 plus 4 is 0, square root of 0 is 0, okay? And what do I get when I plug in -2 into the blue equation? -2 times 2 is -4, plus 1 is -3. This is where I start. The first point I plot is 0, comma, -3. Okay. Now, I don't need to plot all the points in between. The only other thing I need to do is find out where I finish, which is at t equals 6. So I'm going to take t equals 6. I'm going to plug that into the equation, see what we get. Let's see, 2 times 6 is 12, plus 4 is 16, square root of 16 is 4. And when I plug 6 into the y equation, I get 12 plus 1, which is 13. And this is where I'm going to end the graph. Okay, so I'm not going to draw the whole parabola. I mean, you can tell by the graph I gave you, right? I only gave you the right half. So yeah, you're only going to draw the right half. But the reason is because when we pick our starting point is the starting point of the interval, and our ending point is the last number in the interval. And so we have our starting point, and then our ending point is way up here. And we can just go ahead and connect those. Whoa. We can connect those. And let's see if it'll let me erase just that piece. Nope. Okay, so we start and we stop. We put some arrowheads in there. So we know the direction and we're done. Okay. All right, so let me pause here for a moment. Zoom into example 6 and 7. So we've learned this new skill about how we eliminate parameters, and we have to be clever about it, right? There's no one method I can tell you will work super well every time, but we also want to start to think about, if the equation looks like this, what is the graph going to look like, right? So what kinds of questions do we have so far? Any questions? All right. So what we're going to do to finish things off is we're going to take a look at 4 questions, where all we're going to do is eliminate the parameters. Okay. So we are going to just focus on the equation, think about the algebra tricks that might be useful for us here, and how do we combine all 4 of these into equations that are just one equation and have x's and y's, but no t. Okay. So it looks like I missed a bunch of questions in the chat. Let's kind of go back to that. So for number 6, is there another way to justify why it's both directions? If you think about plotting points, like if you plugged in negative infinity, negative 1,000, 0, 1,000, and infinity, you would get something that goes in both directions. Okay. I don't know if that answers that question, but is it a parabola because the degree was different by 1? Okay, so this one, it is a parabola because 1 degree is half of the other one. Okay, so what I mean by that is the degree here. So the degree of y is 1, like the blue equation, and the degree of the x equation is 1/2, because the square root is the same thing as the power of 1/2. So when that degree is half of the other one, you're going to get a parabola. Okay. All right. How is example 6 not limited by the range of the parabolas? Well, if you plug in those values and you're squaring them, tell me a little bit more about that.
So in the x values, it's only going to go as low as -2, right?
Mm-hmm.
And in the y of t equation, it's only going to go as low as y equals 1.
Okay.
Because they're squared, and I'm basically thinking of the x-axis as a 2D, like a 1D version of the parabola in x of t. So it's only going to go from like down and then back up to the positive. So it should be limited by the range of the parabolas at the end.
So what would you modify about the graph?
It has a starting point. It just doesn't have a positive endpoint, but it does have a starting point in the negative where the 2 vertices are going to be the points where it begins.
Okay, so what is the coordinate on the rectangular plane that should be the starting point?
-2. Sorry, wait. Okay, now I'm confused how to find the vertex of the parabolas. the original was, but I think it's -1,
Okay.
right? Like Eric said in the chat.
Mhm.
For t equals 0, it's going to be.
Okay. So what we could say then, right? And I think that's a really good point, right? When we think about plugging in points, we really want that purple part, right? Because if I plug in any number in for t, positive or negative, right? Because all real numbers means pretty much everything is fair game, positive or negative. The smallest value that can come out of here is -2, okay? And if we think about this part over here, same thing, the smallest value that can come out is 1. Other than that, I'm adding numbers, right? It's plus something, plus something, plus something. And so to make this a correct graph, what we should do is get rid of this part, okay? And see that we do have a starting point, right? So here's our starting point. And yeah, it does kind of go forever in the other direction, but it does go in both directions still, all right? But this is kind of like the point where it sort of bounces back and turns around. Does that clarify some questions about number 6? Okay. All right. So let's take a look at these last 4 questions, okay? So in these last 4 questions, let's think about a little bit of strategy, okay? So what would folks do for number 9? Like, how would you get number 9 to be a rectangular equation where there's no t's and there's just one equation? Sorry, for number 9. Number 9. All right, let's take a look at number 9. How might we get rid of the t's in number 9? Okay, subtract. Okay, so Natalia says maybe start here and isolate t and then substitute it in. Okay, I think that could definitely work. What about number 11? Let's skip down to number 11 for a moment. How might we approach number 11? Okay, so maybe going back to like example 5 and thinking about this most common trig identity. Okay. Okay, now let's look at number 10. Now let's look at number 10. So for number 10, How are we going to get rid of those t's? Right, and I think, Natalia, you said earlier, logs and natural log, right? Well, we have a log, but like, how do we get rid of a log? We kindly ask them to leave. Well, they're not super polite, so no. Well, we have a log, right? So natural log is still a log. Right? Log and natural log are the same sort of idea, right? But the opposite or the inverse of a log is exponentials. Yeah, so we might need to go back to our toolkit and think about exponentials and then do a substitution. Okay. Yeah. All right, now let's go back to number 8. What are some thoughts around number 8? Okay, so one idea might be using a natural log. Okay. And I'll say that's a fine and good way. There's actually another way in which you don't even need to use natural log, but you could just make a substitution. Okay. And so what we're going to do right now is I'm going to put you into some breakout rooms. Let's see, what time is it? 11:37. And let's take about 15 minutes to kind of play around with these ideas and see, given the strategies that we've written down here, how we might apply those strategies to get rid of the parameters and write rectangular equations. Okay. Eric, what's your question? No, x of t is the same as x. Okay, x of t is the same as x. Okay, and Natalia, can we allow to divide 3 in number 8? Yeah, you're allowed to do that. Okay, all right. So let's take 15 minutes in some breakout rooms, play around with this, okay? Part of this is I want us to develop this sort of like strategizing, okay? As we prepare to move forward in our mathematical journey, it is one of the things that's like not necessarily on a checklist or on a syllabus, but this idea of being able to problem solve. That actually is what makes a lot of folks either successful or not successful. Okay, but just because you don't know how to problem solve now doesn't mean you won't be successful. It's a skill that you can develop. All right, and so I think it's important that we kind of practice that thinking a little bit. All right, so let's go back into those breakout rooms. I'm gonna stop sharing here. I love all these different ideas. And I'm gonna, okay, I think everyone is back. So I hope that time was valuable. Maybe let's start with number 9. Someone talk me through that process. Did you end up using the strategies that we wrote down for number 9? Yep, okay. So that's going to give us y minus 1 equals t. So everywhere we see a t, we can say x equals 3 times y minus 1 minus 2. Right? I think I did that correctly. You can 100% leave it like this. That's absolutely fine. You can distribute that out if you'd like. Okay, that's also fine. You can also solve for y, and that's also fine. Okay, but I think the part I wanted us to focus on was that process, that thinking of like, how do we get rid of the t's? Okay. All right. One last thing to talk about here. You'll notice that there's no like, what can t be? And so if we don't write it, we're implying that t is all real numbers. Okay. All right, so I think when we were going over these in the beginning, we said, let's set up the strategy for 9, and then I had us jump down to number 11, right? And Natalia pointed out that we could maybe use this cosine squared plus sine squared equals 1. Is that the strategy that folks ended up going with? Yeah, okay. So if we do that, let's see, we're gonna get x over 4 is sine t. So everywhere we see a sine, we're gonna put x over 4. And y over 3 equals cosine. And when we make those substitutions, we'll get y over 3 squared plus x over 4 squared equals 1. Okay. Now this is absolutely fine and good. Okay. If you wanted to remind yourself of what this looks like when we're talking about conic sections, you might write it as x squared over 4 squared plus y squared over 3 squared equals 1. Okay, if we were graphing it, I think that second form might be more helpful. You could think about this in the x direction, I'm going to go out 4 units, and in the y direction, I'm going to go up 3 units. And so we can see there that we have an ellipse. Okay. All right, I was confused on how our breakout was explaining this short. This is a shortcut because you have to square both sides first and then substitute. I would isolate the sine and the cosine and then square it, but it doesn't really matter in that case. So I think what folks were trying to do was like get this sine by itself so that they could substitute it in. And then similarly, to get this cosine by itself. So that's why we divided the 3 to the other side and we divided the 4 to the other side. Does that clarify that, or is that still not quite making sense? I mean, Eric, I think in this case, you could square both sides first. That would be fine. And then you'd have sine squared and cosine squared. Oh, okay. I think the trick to this question really lays in knowing to use that cosine squared plus sine squared equals 1. Okay, and mostly just because we have sine and cosine in the equation, so we want to think about what other formulas we know that involve sine and cosine. Okay. Yeah, I mean, those are definitely possible parametric equations. dealing with just sine or cosine, and the other one might be something else, kind of like how number 10 mixes and matches, right? But I think those don't tend to make quite as many sort of nice shapes that we can do things like find the area of or things like that. So they just don't come up quite as much. Okay. Okay. All right, cool. All right, so let's jump back to number 10 before we finish off with number 8, okay? And so when we're looking at number 10, folks had said, well, let's use the exponential and then sub in, okay? Oh, okay, yeah, that's not correct. So we need to make sure we square things because it's the cosine squared and the sine squared, okay? Thanks for bringing that up. Okay, so for number 10 then, we have y equals log of t. Now, I know this was way back in Math116, but moving forward, we are going to come back to logs and exponents. So what is the base here when I have log 10, but I don't have a number written there? That number is going to be a 10. So I'm just going to write that in. We have a base 10. Okay. And so when we write this in exponential form, we'll get t equals 10 to the y. Okay. So exponential form. Okay. Now, I know that was a different class, and it is important that we remember these skills. Like we went very deep into how to solve log equations and all of that stuff. But when we start thinking about skills that are going to make us successful in calculus, it's this kind of stuff. Exactly what we're doing here, which is being able to reach back into all the things that we ever learned and remember the key points here so that we can apply them to a different context, okay? So now we've isolated our t, we can go ahead and substitute that in, okay? So we have x equals, it's the square root of t, so I need to put square root of t plus 2. And I know that looks weird, like we've not really seen an equation like that, but that's okay. Nobody said you have to solve for y, you can just kind of leave it like that. Okay, the way you did it was square the left equation. Okay, so let's see. If you square the left equation, you're going to get x squared equals square root of t plus 2 squared, which is equal to square root of t plus 2 times square root of t plus 2. Yeah. Okay, so I'm going to say no on that one, all right? But I like your idea of sometimes instead of taking a square root, if we could square it, we could get rid of things. We just have to be really, really careful about FOILing, okay? All right. Yeah, and this one doesn't get rid of all the square roots. I think it actually creates more square roots, so it might not be the best option here, okay? But if there was no plus 2, if you had x equals square root of t, I would 100% do that. All right. So last but not least, yeah, exactly. Or if the root covered the 2, okay? So there's certainly ways that we could use that strategy, but I think in this case, maybe not. Ooh, all right. So how many people did the natural log part? Anybody end up doing that strategy? Or did folks, no, okay. What did we do? Oh, you did, okay. Okay, and where did that take you? Okay, so x equals e to the negative t. Okay, so then you said x to the negative 1 equals e to the negative t. So it sounds like you use that idea that whatever you do to one side, you can do to the other side. Yeah. And you'll get x to the negative 1 equals e to the t, or 1 over x equals e to the t. Okay. Now, I just want to pause for a moment right here, because I'm sure there are some of you sitting out there being like, this isn't even anything we learned. Okay. This ability to work with exponents is going to come up so much in calculus. Right? So if you're sitting here thinking, all right, I'm moving on to Math 150 in the spring, what are some things that I should brush up on? It isn't necessarily going and solving a bunch of really complicated equations. So much of it goes back to like, do you know your exponent properties? Okay, do you know a simple graph transformation? And so I'm just going to write down the name of the topic. All right, looking at exponent properties. If this part doesn't look familiar to you, or you're not sure how you get from one step to the other, I would encourage you to spend some time with exponent properties. Okay. All right, so sorry to interrupt. You said now you've got 1 over x equals e to the t, and where did you go from there? Where did you folks go from there? Substitute. Okay, so everywhere you see e to the t, you put 1 over x. Okay, so you'll get y equals 3 times 1 over x, or I could write that as y equals 3 over x. Okay, exactly. Now, this kind of shortcutting, when we get to Calc 1, I might not write 3 times 1 over x. I might just write it as 3 over x, okay? So we have an answer here. We got rid of the t's and we have x's and y's. So let's maybe go back and explore Yitan's method. So you said you used the log. So tell us what you did. So the y one, you divided both sides by 3. Okay, so y over 3 equals e to the t, which means that t equals the natural log of y over 3. Okay. And then you substituted that, so then you got x equals e to the negative natural log of y over 3. Yeah? Okay. Well, first of all, we're really moving into a realm where not all of the time we have to get it into y equals. Sometimes we can have x equals, and that's okay. All right. Now, I do want to bring back a few of these log properties to help us figure out like how this is the same as the y equals 3 over x. All right, that's going to be sort of another common stumbling point for folks is you like do a problem, you get an answer, but it might not match with the answer key. And you're like, well, how did they get there? Okay, so let's just kind of talk through how we get there. One thing that we should know is that when we have a like a constant in the front, okay, so this minus, remember we can bump that up as an exponent. That was one of the log properties that we learned back in Math 116. And if we use that property, we'll get e to the natural log of y over 3 to the negative 1 power. Okay. Another thing we learned is that e's and natural logs sort of undo each other. So these folks actually reduce, and we end up with x equals y over 3 to the negative 1. Okay. Now, anything to the negative power really means that you switch the sides of the fraction. So instead of y over 3, we really have 3 over y. And if we isolate y, we'll get 3 over x, which matches our equation. Okay. So exponent properties, log properties, all really fundamental for a lot of the work we're going to do in the spring. Okay. All right. So in some ways, I think this is really sort of the perfect lesson to finish up on. For those of us who sort of took this as an entire experience in the fall, where we're looking at all of this algebra, and now we did all of this trigonometry, and we're finishing with a section where the two of those actually really come together, okay? For some of you, that's probably your worst nightmare. You're like, oh my goodness, it never goes away, okay? And for some of you, this might really solidify like the reasons why we do these things, because they're not actually different, but they connect in a lot of ways. And sometimes we have to be really patient about when they come back up again, okay? So the last thing I just want to show you, and you're welcome to kind of look at this on your own time. I actually need to make a correction here. Okay, so I made a little chart that typically I share with my Calc 2 students, okay? Because sometimes folks don't get parametric equations in pre-calc. It's sort of like the last thing that they learn, and so it might be something where they're like, oh, I hope this never comes up again. But I think we've done a good job of sort of exposing ourselves to what parametric equations are. But this is just a little chart that you can fill out if you want. You don't have to think about some of the patterns that we highlighted earlier. So when you see the parametric equation, you could think immediately, oh, this is going to be a line, or this is going to be a parabola, or this is going to be a circle, or this is going to be an ellipse. All right. So a lot of those common shapes, what do they look like? The equations look like when we write them in parametric form. Okay, so I'll let you fill that out on your own time if you find that helpful. This sheet, if you are planning to take Calc 2, might be a good one to hang on to, just so you can come back and think about some of the shortcuts when you're wrapped up in all the other calculus stuff. You can actually focus on the calculus and not thinking about the pre-calculus stuff. Okay. All right, so I'm going to stop sharing. I am going